Okay, so let's restart with the Grover search algorithm. So at this time we have this, well, Matteo, explain what it is.
Yes. Okay, this is the Minicourse keyboard again. Okay, because during the notebook, we were trying to make it fun in some sense. And so the idea is that the problem of Grover here is, okay, you are at, I mean, there is this mongoose, he's at a party, okay, he's partying with the friends, and someone put the sugar in the coffee. And that's a big problem because the mongoose like the coffee bitter. So, I mean, this is the scenario. And so the idea is that, okay, but there is an evidence. I mean, yes, there is something in the coffee that's an air of the guilty person. So the mongoose has an oracle, which is a DNA machine, which can detect the DNA of the guilty person. And so the Grover setup will be to detect which component of the state, so which person in the room was the one guilty of putting the sugar in the coffee. I mean, just for fun, but in general, this will be Grover, okay? Just for explaining the picture.
See, very, very serious stuff here. Let's move on. So, as usual, we open the notebook, and as you know, we have to install all the packages. So this I'm skipping, but we did it before. Again, the KeyboardJIT, as you saw in the previous tutorial, is not really necessary in our setup because we were playing with few qubits, so it makes no much difference. Until you get to something closer to 25 qubits, most likely you'll not see any difference. Or even worse, you see that the KeyboardJIT is slower than NumPy because multi-threading has communication between threads, and this can slow down the computation. So for this setup here, let's keep the default engine that is installed in your computer. And then we start importing some libraries. Now we will use at least those from Kibo, and we also use some general libraries for plotting and NumPy. So let's do it. I will import a random to generate the items. I will import NumPy as NP, and I will import also matplotlib. Import matplotlib pyplot as PLT. And then we go ahead with Kibo, so import Kibo. We imported the circuit and gates as usual. And finally, let's do it already now and import the kiboedu scripts, plotting scripts. So from kiboedu.scripts, import utils and plot scripts. And here for the Kibo backend, I will not do anything. Let me just print what is the backend, so you can compare what you have to what I have. So the difference is that Kibo will try to give some weight to specific backends. If you don't have anything installed, NumPy will be the default. But if you have installed KeyboardJIT, KeyboardJIT will be the default. So as you can see here, when executing these imports, I get this message saying that the system is using KeyboardJIT because KeyboardJIT has a higher priority than NumPy, and the CPU is the platform that we are using in this configuration. Okay. Very good. So is that okay? Imports? Good. So now let's move down. And the goal here is to create all the combinations, as we did before in the first tutorial, for a system composed by 5 qubits. So let me put the size of the problem will be n equal 5, so 5 qubits. We can also define some number of shots that will be used during the notebook, during all our computations. So n shots in this case can be something like 1 million. But you can tune it. I'm doing 1 million because I don't want to see huge statistical uncertainties. I prefer just to get something closer to the exact simulation. And then we generate all the compositions. So we generated the bit string list. This is exactly what we saw yesterday. So you do bit strings equal to utils, generate a bit string combination, and then we set the number of qubits n. as argument. And finally, we print the bit strings. So you can see all the possible states that are inside my system. Okay. So following these slides, if I ask you how many items do I have, or how many items can I store using 5 qubits, well, the answer will be obviously 2 to the n. So I can have, in this case, 32 elements, right? And you can compare this 32 to the size of the bit string. So if I print 2 to the n, and then I compare this to the length of bit strings, you see that both match. So fine, I can store 32. If I increase the number of qubits, all this discussion will be scaled to 2 to the n, where n is the new number of qubits. Okay? Good. So now let's generate the list of people. So following the metaphorical example that Matteo presented, finding the guy that put the sugar in the coffee of the... we can do it in multiple ways, but here in Python there is a class that you can install by doing pip install faker. So if you do that, the faker package provides a method that will generate fake names, and those fake names can be used for the purpose of this exercise. So I do pip install faker, and then I can create a fake import and create a fake. So from faker import faker, which is the class from our package, and then we allocate a fake variable which is initialized by the faker class. So this is downloading the faker package and creating the fake variable. Now it's time to generate the names with this faker object. So we can do that very easily by just saying that we can create a list of names. And the list of names, we can populate it by doing a for loop. So for I in a range, the 2 to the n elements. For each element, we do names.append, and here we put fake.name. So the fake.name is just generating a name, usually a person name in English with its surname. And now I can print the names. Okay, so you see here, what you are seeing in this list of names is a Python list where names are strings, and we have 2 to the 5 elements, so 32 names. Now the point is that we have to implement the search, so at this point we have to identify, decide more than identify, who is the candidate that we are looking for. And for this particular example, we are just selecting a random name, in particular the one that is identified by the index 11. So if I say guilty index equal to 11, then I can print the name of this object. So I can then print f guilty index is the guilty index. And then I can do the same for the name, so I can convert this number into name. So guilty name of guilty index. Names, sorry, yes. And then we can also do the corresponding to state bit strings guilty index, close parenthesis. Okay? Are you familiar with this notation? I mean, we are always using the Python f string printing, right? So we put the f in front, And when you put the f in front, then you can automatically replace in the string the variables that we are using by putting the brackets. So this is a very short way to just perform a replacement. So by doing that, for example, here you get the guilty index is 11, and then guilty David Daniels, which is the name of the guy that we decided will be our target, corresponds to state 01011. Yeah, you might get a different name because this fake class is random, so you might get a completely number. But for the purpose of this exercise, the most important thing is to know the state. So in this case, it's 01011. Okay. Now, the Grover algorithm, as you know, as we mentioned before, is composed by half of the system that is created in a maximally superposition state, and then the ancilla. So we have to do that, and we have also then to define the unitaries UF and US, and attach some measurement gates at the end. So let's do that. Here you have all the explanations, but in principle it's pretty simple. We will create a function at the end, call it def build initial circuit, or initial layer in this case. So the build initial layer is the function that is responsible to build the initial superposition in a Grover circuit. And it's quite simple, no? Because we know we have to create n to n plus 1 qubits. We can do that by saying C is equal to circuit equal to n plus 1. So we have our 5 qubits plus 1, the ancilla. And then we prepare the state into the ground position. So you have this for all the possible qubits of my system. So to do that, we can do c.add gates and apply the x Pauli at the n qubits, so the last one. And the superposition will be done by just performing a for loop for q in range n plus 1. We go ahead and attach C to some Hadamard gates. So these last two lines, they correspond to the S ket that we described in the slides.
And the minus, of course.
Yes. And the minus for the ancilla, no? Good. Okay, is everything clear? So you see it, so you have here Hadamard for everybody, plus the X Pauli for the ancilla in a n plus 1 circuit. So now I return C, and that's done. So I have my build function that can be used now to generate Grover-like circuits. So this is the initial layer, and we are doing this split between initial and the final. So I mean, this comment goes upstairs. So this is the function for the initial superposition. While here downstairs, we can define another part of the circuit that will build the final layer. And the final layer is an object that contains obviously the same amount of qubits, so I have to create another circuit with n plus 1 and apply measurements. So that's the goal, just measure. So I can do that by creating C, circuit n plus 1, and then doing C add the measurement gates. So you have gates M, and if you remember the first tutorial, we can use the Pythonic way to automatize the list of objects where we are applying the measurements. So you do star range, and inside the range we apply the number of qubits. So in this case, n. Obviously, we don't care about the ancilla, so we are just measuring from 0 to n. When that's done, we return again C, and now we have the both objects. Okay. Good. So let's go on down. Now, what's the goal? The goal is to create a composition of the first layer, the initial layer, and the final layer. As we discussed it yesterday, in Kibo we can do that very easily by just using the plus operator. So my final circuit C will be an object which is composed by the build initial layer with n qubits plus the build final layer composed again by n qubits. And now I can print my circuit and check if the layout makes sense. Okay. So the draw is showing that there are there are the qubit 0 to qubit 5. So there are 5 qubits that are used for the first n half of the system, and then Sila, which is here downstairs and represented by the Q5 qubit. The first 5 qubits are initialized in the superposition state by applying the Hadamard and then the measurement, while the ancilla qubit is first prepared into the X Pauli and then Hadamard. And we don't do any measurement because we, at this point, don't use it. Okay? Good. Now, let's generate some plots and see how the state looks like. So if I do plot scripts dot plot input or register amplitudes, and I send here the simulation results of my circuit dot state, so the analytical solution to the state, this will create the plot that you see here. So I have the state visualization. In the y-axis the amplitudes, in the x-axis all the possible 32 combinations. And as expected, the first part of the Grover algorithm is just creating an equally distributed set of amplitudes for all the possible combinations, for all the possible directions. Now our job is to make sure that we can flip the guilty index object, which was, if you remember, the state 1011, right? I think 01011. So we have to apply the UF, construct a unitary UF that can do this job for us. So flip the guilty index. Now it's important to highlight that here I'm doing a state simulation. However, I could do exactly the same plot by replacing the C dot state with the shots. Now I can just ask the system to generate measurements and a sample from shots. And this is exactly what we can do here downstairs. We can go and write down the plot script. Yeah. So plot scripts dot plot Grover probabilities, and this function will automatically do our request. So we can just send the circuit and the number of shots, and it will be executed, and you can see here the result. No. Again, the probabilities, they are equally distributed. You see that there are some small shifts up and down due to noise and due to the fact that we have only requested 1 million shots. So if you wanted to reduce these fluctuations, you have to increase further the number of shots. Yes.
These fluctuations depends on the machine that you're using.
No. Here is just a sampling. It's a theoretical where we are doing. You have the final state, the theoretical state vector, no, and then we do rejection sampling. So you select how many trials do you want to do, how many random numbers, and then you just collect in which state each qubit will fall. Given that we have 32 combinations with 1 million, we are covering pretty well, but there is still some variance, no? And you can quantify the variance now by.
But it can depend on the n shots, I suppose. So if in your machine you have a different number of n shots, you can have different distribution of this guy.
Yeah, because this is, I mean, from the theoretical perspective, it's just a numeric Monte Carlo then that you are doing. But from the experiment, you have the statistical plus the systematic, and the systematic will make a huge difference like this.
So the probabilistic part of this is due to the fact that you are making the wave function collapse. So sometimes solution, sometimes in another one,
Yes.
depending on the state.
He defined the N-shots as 1 million
Indeed. Yes.
to change everything.
Yes, to make it very similar to the exact case. But this is not depending on the technology you use, because you have your trapped ions, your superconducting qubits, whatever. You just know that you need to repeat the experiment the n shots time you have. So that's a choice of the user.
No, yeah, but I think that the question was about the machine, the computer, no?
Yeah, like
I see.
if I like my machine gets a simulation totally different than yours. The fluctuation depends on it.
No. Shouldn't be like this. We fixed the variance of this sampling. So basically, what we are doing is sampling from the final state with some specific standard deviation of the distribution, or with a Gaussian distribution from the. They were asking about, for the Zoom people, they were asking about the fact if these fluctuations change if you change the machine, like your laptop, our laptop, but no, it's not the case. We fixed this random generation.
Okay, but you are talking, just to understand, because if you have a different random seed generators, then obviously the numbers will fluctuate in a different way, okay? That's what the library does. Okay. Okay, so given that we have the probabilities, now we can move further and create the oracle, so the UF function. So if you remember, the goal is to define this UF operator that flips the sign of the state if the state is the one that we are looking for. Otherwise, it doesn't do anything.
Before you move on,
Yeah.
let me make a question, because I'm kind of lost here.
Yes.
We are trying to find the guilty guy.
Yes.
So when we are doing our search algorithm, we already know the guy.
Mm-hmm.
So what kind of search is this where we are looking for something that we know?
Mm-hmm.
I'm not grasping this detail.
It's like pedagogical explanation, and so you know it.
Yeah.
In principle, this kind of exercise should be done in the case in which you don't know. You just open your Python script, I give you the oracle, and then you should execute the oracle, and you see at some point.
Okay. Someone that gives me the oracle already know the thing.
Yeah.
We know everything because we are building also the oracle. The
Okay,
Exactly,
okay.
exactly.
Thank you. Now
Yeah.
it's very.
But this is one. Yeah, but this is just one way to do it. The other way is that you define an observable of your system that you would like to maximize, for example. No? For example, I'm looking for a state where my entropy is very high, or is the largest as possible, or is some state that can do some entanglement or something like that. So I can define a specific observable that will be tested at each step of my Grover algorithm. No? And this will be the loss function of my system. Right?
Okay, it serves to maximize energy.
Exactly. Exactly. So you can try to the oracle can be even built in the process, but you have to establish what you are looking for.
In the perspective that Matteo gives to us is just like a key distribution, something like you can distribute a key to someone to encode something. But in your perspective, like you have a now you need to
Yeah.
maximize something.
Yeah, exactly. Which is more, I mean, my perspective is a little bit more equivalent to the classical approach. You know, in the classical, if I give you a list of objects, usually you know what you are looking for. Because you ask, I'm looking for an item which is with this specific color or with this specific spin value or whatever, no? But I don't want to search over n squared times items. Exactly. So
Now
this can be done too, but you have to define the proper observable that might be well integrated in the Grover algorithm if you are.
Thank you so much.
The other problem is that we are not using the oracle like an oracle. We are using it like something we know. That's not the usual way.
Now I get it.
Good. So let's do that. Let's do the first approach with this more pedagogical system where we know the guilty index, so we can define a function that is called the build oracle. And the build oracle is a function that, for the purpose of this exercise, knows what is the guilty index and the number of qubits. So here, the first thing to do is to extract the bit string that represents the Guilty index. So we can define the bit string equal to bit strings Guilty index. And then we can design our circuit with the UF operator. So we create first a C equal circuit composed by n plus 1 objects. We can, I mean, for the purpose of this exercise, we just create a zero list that will be populated in the next. And what we do is that we loop over all the elements of my desired bit string by doing I, which will enumerate the element, so the qubit that is activated, and where bit corresponds to the value of the bit string. So this will be from I, comma bit in enumerate bit string. So just a repeat again. So I'm doing a for loop where I'm going, the bit string is 0, 1, 0, 1, 1, okay? So each element is pointing to a specific qubit value. If I do for I, comma bit enumerate bit string, the I index will count the qubit number. So it will be qubit 0, 1, 2, 3, 4, or 5. While the bit corresponds to the value that we should expect, ground state or excited state. So in this context, if the bit, the bit part, ground or excited, is equal to ground, in this case it's a string, so we have to write in this way, then we will append to the zeros array the value, the number of the qubit. So we know that the bit 0 is in the qubit I. And after doing so, we can attach to my circuit some gates. So I can do circuit.add gates.xq for q in zeros. Yeah, I see. No, I do. Let's change it because otherwise it's very confusing. Circuit. Okay.
So are you familiar with enumerate and this kind of loop here? Yeah. Okay.
Inside that, I will go from 0 to 5.
Yeah, I use 0 to 5. Yeah.
This way it doesn't go to 32 because it's every the length of bit strings.
But here we are playing just on the one bit string.
Mm-hmm.
Oh,
Only one, the
That
guilty.
here
Yeah.
the guilty index will create, I mean, you extract the bit string which is 0, 1, 0, 1, I don't remember.
Yeah, I can show you.
Okay.
So if you do this,
Okay.
and we print I and bit, sorry, obvious now. So I have to replace this with, yeah. So here in the first column, number of qubit, the qubit number, and in the other column, the state, the 0, 1, 0, 1, 1, okay? Great. So now what we did is that we have applied X Pauli only on those qubits where we have a 0 bit. So why you're doing that? Because, well, the goal is to flip, no? To flip the state that you're looking for into applying the minus sign. So, yeah, exactly. So here we are triggering only if the control state is equal to the excited state, to 1, 1, 1. Now, to conclude this operation, we have to take our circuit and add another gate. So we can have add gates.x with q equal to n, which is the ancilla, controlled by the range of any qubits. So this is mandatory because it's the way we are connecting the ancilla to the other qubits. And finally, the last thing is to take again our circuit and introduce another set of X gates for Q in zeros.
target amplitude. The oracle should flip the correct amplitude, which is not, which is not 1, 1, 1, 1. It's something different. It's 1, 0, 1, something. But the multi-controlled operation is able to perform some operation, indeed, only when the control state is 1, 1, 1, 1, 1. So since our state is not 1, 1, 1, 1, we want it to act like 1, 1, 1, 1. So we are basically swapping the zeros and the ones such that the target state becomes the 1, 1, 1. Then we apply the multi-controller NOT, which is triggered by that state. But then we need to reconstruct the original state because we want it to be in the future 1, 1, 1, 1, but we want it to be back the original one. Was clear? Or not?
Yeah, it's a bit tricky, but you're doing this. This operation of changing those qubits that we need because they are at 0. So we plus them in the excited state, and then we try to project them back. So let's do some plots. So maybe this becomes a little bit simpler to understand. So if you go downstairs here, and I write down my C circuit by doing Butte oracle, and passing the number of the Guilty index and the number of qubits, and then printing the circuit. Hopla. Yeah, it's here, controlled by. Yes, yes, Mr. Perez, yes. You're right, thanks. Close this, and this, yes. Okay, here you go. Okay, so this is our oracle. It's just manipulating the state and projecting it into the one that we need. No? Now, given that we have the oracle, we can go ahead and construct the final circuit. So in this system will be composed by the initial layer, the oracle, and then the final layer. So we do C equal to build initial layer with n qubits plus build oracle with the Guilty index and the qubits plus build final layer with number of qubits. Okay, so here, remember, the first column that you see is the state preparation. So the maximum superposition plus the ancilla. Then what we do is that the ancilla goes ahead with the Hadamard, while the other qubits, they work with the oracle UF. So this object here that we have created upstairs is now introduced directly as a layer of our system. And finally, we measure. Okay? Should I go upstairs and show you again this? Yeah. Okay.
Any problem in case?
Okay? Good. So now, what we do next? Let's try to measure and see how the amplitude looks like. So I go down. And here we do plot scripts dot plot input register amplitudes. And we pass C dot state. So the exact simulation. And here you go. Okay, so with this specific oracle, now we are able to flip the state 01011, which is our target Guilty index.
If you don't apply the X gates, here you will have the 1111 flipped.
Yeah, we can do that. Huh?
Yes.
Yeah. I mean, it's clear that this behavior is clear, right? Is what we discussed before. So we are just flipping the amplitude for the omega state that we're looking for. Yeah. quale vuoi togliere? Vuoi togliere?
Se togliamo tutte queste x,
No.
dovrebbe venire fuori che si flippa solo il... questa però la devi lasciare, la control not. Esatto.
Yeah, so now let's try to repeat the same exercise, but now we remove the 2 layers of Pauli axis that we have applied. Let's see what happens. So if I just keep the controller, so the circuit now looks like a single controller. I can build my system again and this becomes much simpler. I have just a single controller. But now if I plot, you see that I have flipped only the last layer. Now the last state, which is the one corresponding to all qubits in the excited state. So you see that that's exactly the game. If you apply the X to all qubits, obviously you are bringing all the qubits to the excited state. With the layer where we loop over the bits, only to those bits where we had a 0, then we can really create a filter that will flip the target state, the 0, 1, 0, 1, 1. Yeah. Yeah, in this plot, no. In this plot, it is displayed. Is this one here? Okay.
If you consider also the state of the ancilla, you will see that you will have double the number of the amplitudes because you have the same state plus the 0 and plus the 1. You should consider all the possibilities, which are to do the 6. And then you will see that half of the time they will be up and half of the time they will be down, because the ancilla was preparing in the minus state. So sometimes it's positive, sometimes it's negative.
Something like a counter.
Yeah. We have another notebook in which we show this. But for the sake of the Grover, we just show the input register because the important point. But if you consider, you can also plot the amplitudes considering the ancilla, you will see that you will have a lot of duplicates with minus and plus sign, due to the fact that the ancilla is half of the time minus, half of the time plus.
Okay, so let's go back and recover our original oracle. So now we are back to the situation where the target guilty index state is flipped. The next step is to plot probabilities. And as you can imagine, if I generated the probability plot associated to this set of amplitudes, I will not observe anything special, no? Because probabilities are positive defined. So let's do the plot scripts dot plot Grover probabilities, the circuit and the number of shots. And here we go. So at this point, you see that all the effort at the end, at this stage, is not it has not converged yet. Okay. Any questions so far? Great. So before going to the second break, let me just recap what we did since the beginning. So we have imported Kibo. We have created the bit string combinations for all the 5 qubits that we have selected. We have then generated the guilty index that corresponds to the state that you are looking for. In this particular scenario, the 0, 1, 0, 0. And then constructed the first part of the circuit, which is equivalent to the phase kickback example with the maximum superposition of Hadamard's and then Scylla qubit, and the oracle UF. So now what we have to do after the break is to define the US operator, the diffusion operator, and then start to study how many interactions of the Grover algorithm I have to do in order to amplify the results and modify what we obtained here. So we don't want to see a flat distribution, but we would like to see that the probability associated to the state 0, 1, 0, 1, 1 is very high, much higher than any other state, right?
An important thing, maybe we prover is not deterministic. We are going to push this bar to be higher and higher, but we don't have the, I mean, we are not sure we are going to get the probability, the correct solution with probability equal to 1 or 100%. For this reason, we need to move the vector and to perform many inversions in order to be as close as possible as the correct solution. And that is the optimal number of iterations. Oh, sorry.
Would be necessary that this number was an integer, right? Because we have an integer interaction, but that number is not necessarily integer.
Yes, indeed. From the theory, you know there is an optimal number of solutions, which is true under the assumption also that 1 over the square root of m is very small, because we did this, you remember the arcsinus of theta equal to theta. This is an expansion, but it's true only in that case. So if you have a lot of items on which you are searching on, and you came out with this formula, which is not integer, but we are speaking about number of iterations, so we need to make it integer. Since m is very high, taking the lower approximation or the upper approximation is just a convention. But we take the pi over 4 times square root of m because typically we do like this.
But this is the reason why we can be 100% sure we find them.
Ah, yes, also, yes, you're right. Yes, of course.
Okay, good. Any other questions? Right, so then we make a break and we reconvene at 4:25.